In this section, 4.5a, we'll be looking at what's known as the fundamental theorem of calculus, or at least the first part. And our objective in doing so is that we're going to examine how we can connect everything that we've been learning so far in this unit. Specifically, how can we find the exact area of a curve of an arbitrary function, and how does that relate to antiderivatives? So, suppose we're interested in measuring how far a toy car travels over a given time interval, from let's say t1 until t2 over a flat track. This is what we did in our inquiry activity. The most straightforward way of measuring how far this car travels would be simply to measure the initial position of the car at t1 and the final position of the car at t2, and then take the difference in those positions. Delta x equals x of t2 minus x of t1. The other way that we could do this, as we saw in class, is that we could track the car's velocity as a function of time, and then we could calculate the area between the velocity function and the time axis. The idea being is that the area, height times base, gives us v times delta t. If we recall a little bit of algebra here and a little bit of physics, we know that the average velocity is equal to the change in position over change in time. So if we solve this equation, we're going to get our change in position equals v times delta t. By comparison, that tells us that our change in position, comparing these two equations right here, our change in position over a specific time interval is going to be the area between the velocity versus time graph over the specific time interval of interest. If we extend this concept a little bit further, okay, what we can see is that for an arbitrary function, instead of just a rectangle, we can calculate the area beneath an arbitrary function of velocity as a function of time by approximating this area with many, many rectangles over a time interval of interest. So in this case right here, the more rectangles we add over this specific time interval, the more accurate answer we're going to get for the area between our velocity curve and our time axis. And hence the more accurate answer we'll get for how far our car has traveled, our change in position over this time interval. So what we can write here is we can write that our change in position is equal to the limit as n goes to positive infinity of the areas of each of these rectangles, each of height vi and of width delta t. Again, the idea being is that if we let n go positive infinity, the area of each individual rectangle will approximate the curve better and better and better until we obtain an exact answer. But what we recognize right here is that this definition, this limit definition, is the idea behind the definite integral. The limit of a Riemann sum is equal to the definite integral from t1 to t2 of our velocity function. So what we have here is we have two different but equivalent ways of determining how far our car has traveled. We can either calculate the definite integral between a velocity versus time axis, velocity versus time curve, using motion sensors, or we can simply calculate the change in position from x of t1 to x of t2. Now, this way in practice is a lot easier, calculating the change in position just by measuring the initial and final positions is a lot easier than calculating the area between the curve. However, the application here to calculus is still very, very useful. So what we can take note of right here is that because these two are equivalent, we can say that our change in position from t1 to t2 is going to be equal to the definite integral from t1 to t2 of our velocity function. So again, even though this idea right here seems overly complicated in practice, we could just, again in practice, we could just measure a change in position with a ruler. The idea here is we can extend this to calculus to a wide variety of scenarios. Specifically, in our first instance, the idea of connecting the antiderivative to a definite integral. So what we can take note of right here is that right here we have a position function. All right? Our change in position function, or our change in position, is equal to definite integral of the velocity function. So what we can take note of right here is that velocity is the derivative of position. And hence, as a result, position is going to be the antiderivative of velocity. So what this tells us right here is that the change in an antiderivative of a function, say our antiderivative is x, okay, is going to be equal to the definite integral of that function over a specific interval of interest. In this case, our function being the velocity function. If we extend this now to arbitrary functions, not just to example physics, but just more generalized functions, what that gives us is that the change in the antiderivative over an interval from a to b is going to be equal to the definite integral from a to b of the function f. Okay? In practice, what this means is if we want to evaluate the definite integral of a function f from a to b, we can first calculate the antiderivative or determine the antiderivative of this function f, and then determine the difference in the antiderivative from a to b. So this brings us to the first fundamental theorem of calculus. It states that if f is a continuous function with an antiderivative uppercase f, the definite integral of lowercase f over an interval ab is equivalent to the change in the antiderivative uppercase f over the aforementioned interval. Again, in terms of reiterating concepts, our definite integral of a function lowercase f is going to be equal to the change in the antiderivative from a to b. So again, in practice, if we want to evaluate the definite integral, now instead of using rectangles approximations, all that we have to do is find our antiderivative and determine the change in the antiderivative from a to b. So, in terms of interpretation, this gives us a new interpretation for what the area between a curve f and the x-axis represents. Specifically, the area between a curve f and the x-axis over an interval ab, the definite integral, represents the change in the antiderivative uppercase f over said interval, which is what's conveyed to us right here. This is our definite integral, represents the area between f and the x-axis, and it's mathematically equivalent to the change in the antiderivative over our interval of interest. So applying the first fundamental theorem of calculus. The first thing we need to do if we want to apply the first fundamental theorem of calculus in order to evaluate definite integrals is first we need to determine the general antiderivative of the integrand. We do not have to use c in this case because c will cancel out in our calculations. Once we have determined the general antiderivative, okay, we calculate the change in the antiderivative over our interval of interest. So let's take a look at an example right here. Suppose we want to evaluate the indefinite integral of x cubed plus 2x from x equals 0 to x equals 3. All right, and boo, I made some typos here, so this looks quite ugly, but 0 to 3 here. All right, so the first thing that we're going to do here is we need to determine our antiderivative of x squared of x cubed plus 2x, okay? So the antiderivative of x cubed plus 2x is going to be x to the 4th over 4 plus x squared. So now what we're going to do is we're going to evaluate this antiderivative, the changes antiderivative from x equals 0 to x equals 3. This bar sign right here with the x equals 0 and x equals 3 is an intermediary sign that's used to indicate that we've evaluated our antiderivative, which we've done, but we have not yet evaluated the change in our antiderivative. Okay? So this indicates to us a nice little intermediary step that we're going to, after we've calculated our antiderivative, we're going to calculate the change in our antiderivative from x equals 0 to x equals 3. So, what we're going to have right here now is we evaluate our antiderivative x equals 3, so which is going to give us 3 to the 4th divided by 4 plus 3 squared. And now we're going to take the difference, we're going to subtract our antiderivative evaluated at x equals 0. Again, we're taking the change from x equals 3 to x equals 0. So we're going to have x equals 0 to the 4th divided by 4 plus x equals 0 squared, which is just going to give us 0 overall. So as a result, our overall antiderivative is going to be, the overall change in our antiderivative is going to be 81 over 4 plus 9, or 117 over 4. So again, I determine the general antiderivative, and then I determine the change in the antiderivative at the specific points of interest, x equals 0 and x equals 3 and x equals 0. So now let's look at determining values of a function using the fundamental theorem of calculus. So an alternative but equivalent way of stating the fundamental theorem of calculus is that if f prime is the derivative of a function f, then the definite integral of f prime over an interval AB is going to be equal to the change in f from x equals a to x equals b. Again, the idea right here, okay, is that the definite integral from a to b of a function is equal to the antiderivative, changing the antiderivative over that interval a to b. So if we have a derivative f as our integrand, a derivative of f as our integrand, then the antiderivative will just be f itself. So how we can use this right here is if we want to evaluate the definite integral of f prime between x1 and x2 of f prime dx using the graph of f prime, say we're given a graph of f prime, what we're going to do is we evaluate this integral using the graph of f prime, just like we did in 4.3, just evaluating the area between the curve and the x-axis. Okay? The second thing that we're going to do is we're going to set the definite integral equal to the change in our change in f, okay? Meaning f of x2 minus fx1. As a result of the first fundamental theorem of calculus, we know that the definite integral of f prime is going to be equal to the change in f. Okay? And then lastly, we'll solve the last equation. We'll rearrange the last equation to solve for f of x2, all right, if we're trying to determine what f of x2 is. Which means in this case, we're going to add f of x1 to both sides. Although this seems a little bit esoteric, this is nothing more than an application of the change equation, okay? Specifically, we know from algebra that the final amount of a quantity, let's say f of x2 is going to be equal to the initial amount of a quantity, f of x1, plus the change in that quantity, which is represented by the definite integral. Again, remember, definite integral represents a change in our quantity, in this case, the function f. So let's look at example here. Example 1, determining values of a function f using the first fundamental theorem of calculus. The graph of a derivative f prime of a continuous function is shown at right. If f of 3 equals 1/2, what is f of 5? So first thing we can note right here is that we're interested in the integral from x equals 3 to x equals 5. So we evaluate the definite integral of our function f from x equals 3 to x equals 5. Or excuse me, of our derivative f prime from x equals 3 to x equals 5. So we calculate out that area, which is going to give us minus 1/2, 1 times 3 plus 1/2, 2 times 3, which as a result of calculations is going to give us just 3 over 2. So next thing we recognize is that by the first fundamental theorem of calculus, this definite integral from x equals 3 to x equals 5 of our derivative f prime is going to be equal to the change in f, the antiderivative from x equals 3 to x equals 5. So as a result, we're going to set 3 over 2 equal to f of 5 minus f over 3. So we know f of 3 is equal to 1/2. So we can substitute 1/2 for f of 3, which allows us to get the equation 3 over 2 equals f of 5 minus 1/2. So as a result of solving for f of 5, we're going to get that f of 5 equals 2. In a way we can check to make sure this makes sense. We know that our definite integral here is positive. We have a positive area, which means that our change in our antiderivative must be positive. So as a result, if we start at f of 3 equals 1/2, that means f of 5 must be greater than 1/2 since our area is positive, which we can see in the end right here where we get an answer of f of 5 equals 2, a value that is greater than f of 3. And these are fundamental applications of the first fundamental theorem of calculus.